Are there any announcements that need to be made, or? Okay. So is there actually a discussion session this afternoon, or? Okay. I'm not sure I'll be able to be there. Okay, so in the latter part of yesterday's lecture, we looked at one particular one-loop integral which we could integrate explicitly, and we saw some of the special functions that arise. And in fact, at one loop, those are the only special functions you need, just the dilogarithms in addition to the functions you already know. But at higher loops, there'll be more functions, and I'll mention them in a little while. But most integrals you can't really integrate directly, and so we need other techniques. And there are a number that have been used over the years. I would say the one that's probably the most popular these days is that of differential equations. And really doing this fully, giving a complete introduction could take a course on its own. So instead, I'm going to give, I don't know, about a half-hour introduction. And the idea is actually a very old one. It goes back to the early 1990s. But there were a number of improvements that were discovered or invented about a decade ago that made it a much more powerful tool and ultimately a much more popular one. So the basic idea is that we're going to differentiate with respect to some kinematic invariant or set of kinematic invariants. We have some integral, and that's going to produce something. And that something, in general, will have a lot of integrals. Well, first of all, it'll attack the integrand, and then we can spread it out into a set of integrals. They'll all be Feynman or Feynman-like integrals, but they're not necessarily integrals that are actually physical ones or ones that we're interested in. But we already know, we saw yesterday that we have this very general technology of integration by parts that can take whatever we have on the right-hand side and turn it back into basis integrals. And so, in general, one is going to attack with all the different basis integrals with a variety of derivatives with respect to invariants, and that'll produce a set of complicated things which one can reduce back to basis integrals. And so we're going to get a system of differential equations. Now, what I'm going to show here is a very, very baby version of this. And we're going to look at an integral which, especially given yesterday's lecture, you should be able to do by Feynman parameterization on the back of an envelope, namely the one-loop box. So we're going to want to differentiate with respect to invariance because, in fact, the integral ultimately is a function of those invariants. And here there would be two of them, S and T, but we can actually rescale one out. We'll do that in a little while. And so there's really just one dimensionless ratio in which this integral appears. So this is the 4-point one-loop integral. And again, we are going to do it in dimensional regularization. That's actually important to the modern version of this technique. So we want to differentiate with respect to invariance, but what actually appears inside the integrand is just going to be, are going to be momenta. So we have ddl 2 pi d L squared L minus K1 squared L minus K12 squared L plus K4 squared, and we're just going to consider the unit numerator. Of course, this approach doesn't really care if the numerator is unit. You could apply it to more complicated things as well. So one way of translating, so we need to translate from, let's say, a derivative with respect to s to derivatives with respect to the momenta. Could do it by the chain rule, just being careful about momentum conservation. But it's probably simpler just to write out an ansatz. And we can see that S could express, I mean, we've taken 1, 2, and 4 as the basis momenta, squeezed out K3. So S is naturally expressed as K1 plus K2 squared. So it's natural that d by dk4 should not appear. And then you might guess maybe that you could write an ansatz just in terms of K2. I mean, the most general ansatz you would write down is some sum over the Cij, Ki, dotted into the derivative with respect to Kj. But we're going to take a simpler one and just write d by ds as just Ci times Ki, and only have derivatives with respect to K2. So we can, we have a bunch of constraints. So for example, we want d by ds of K1 squared, which is actually 0, to stay 0. And that's going to be automatic because K1 doesn't depend on K2. And likewise, another constraint that we want to keep is also automatic. So we also, of course, want K2 squared equals 0. That's not automatic, but it just gives us C1 times S minus C4 times S plus T equals 0. Again, there's d by ds of T should be equal to 0. So d by ds of K1 plus K4, again, that is automatic because we've eliminated K3, so there's no K2 either. We just need to insist that the normalization be correct, and that gives you another equation, which I think has the form, let's see, C1 plus C2 minus C4 is equal to 1 over S. And so we can solve these equations. And then we have a differential operator that we can apply directly to the integrand. So now we're going to apply d by ds to I4. And I'm not going to write out the algebra, or I should say I'll write it out just graphically. So this is d by ds of the box. Let me just, for completeness, label the legs. So we have T over 2, whoops, slippery. Does anyone remember what the dot signifies? Yes. The answer was that the dot represents a doubled propagator, which is correct. And if you were unfortunate enough to start differentiating objects like this and got a triple propagator, you just put another dot on. And I don't think in the literature anywhere I've seen more than 3 dots on a line, but if you're going to put many, many more of them, you might some notation like with a dot and something in brackets to indicate how many dots are there, or a dot raised to some power 2s, s plus t, to 1 and 4, and that should be 3. And then we have a bunch of other triangles. Write it here, 2s plus t. So thankfully, we actually do have one term on the right-hand side, which is the original integral. But it wouldn't actually matter if we had none, because we're going to convert them back to the integrals that we care about. There's essentially a symmetrized version of one of the triangles. So this term is, of course, the integral that we're interested in. Everything else is a new integral. On the other hand, the triangles are, in a certain sense, elementary. You could just do them directly. So the question is, can we actually turn this into something that we know? And if you can do that with the IBPs. I'm not going to work them out. It's not very complicated. It's a great learning exercise if you are trying to get started with either Fire or Kira to do precisely this system, because it's also a system where you could pretty much do things by hand, and so you can understand what it's doing. So for example, we have this relation. So the box with one dotted propagator, we can write in terms of our original box. And let me get the coefficient right here. Let's see, d minus 5, d minus 3. And then there's a d minus 6, st squared. And this is a t-channel bubble. So this is, in this case, an elementary integral, but in general, none of the integrals need be elementary ones. There should be an equal sign there. And some of the triangles, no great surprise, because if you actually do the one-mass triangles, they pretty much are just going to be a power of the invariant, so that's already obviously proportional to a bubble, so this one is in fact just going to be a bubble, and you could actually work this out, this coefficient, without resort to IBPs. And again, another t-channel bubble. And finally, we are going to get something that is in the S channel. And there's something similar for the remaining triangle. So if we now collect all the different terms, then we end up with a differential equation that says that we have S plus T plus switching from D's to epsilons times the box itself, and then there are two bubble terms. So bubble, BUB stands for bubble, not any great shock, I'm sure, to anyone. And it's just the channel in which it's in. They're both S and T channel bubbles. So the bubbles, of course, are elementary integrals. We would need a boundary condition for the integral, but and then one could just go ahead and solve it. But what, rather than doing that, I guess, leave that as from this form as an exercise. But we want to look at the kind of general form that one might get. So, as I said, in general, we have some number of master integrals. We have to have a one or more differential equations for each one. And those will, again, be ultimately expressed in terms of the master integrals. So the general form we're going to have, so f here is our vector of master integrals. The dimension depends on the number, and the number depends on the problem at hand. It depends on, can depend in a very delicate way on the external masses, the internal masses, the topology of the top-level graph. So it's going to be of this form. A here is, so if this thing is, let's say, an M vector, then this now is an M by M matrix, and it's a rational function of the invariance and of epsilon. So now here I was working with a dimensionful one, but it can be convenient to actually work with dimensionless ratios. And of course, the box integral itself is just going to be a function of one dimensionless ratio, just T over S. And so we can translate our equation to one in terms of chi. So this notation is just going to mean d by dv, or in our case here, d by d chi. And we can write this as follows. So this has the form of a difference. And so I'll leave as an exercise to work out the other derivative here that one has d by dt. And you could do it by the chain rule, or you could do it by writing down an ansatz. So there's an overall dimensionful power of an invariant. That's just from the dimensional regulator. And so we can define 3 functions just to scale out that overall dependence. So the dependence inside, if you remember yesterday, is some invariant to the minus epsilon, so we're going to multiply it by something to the plus epsilon, and then we're going to multiply by what turns out to be the denominator, but just something that soaks up the correct dimensions. And similarly, F2 will take multiplying the S-channel bubble, and F3 will do this for the T-channel bubble. So these are now dimensionless objects, and we can write down the system of equations. Here it's a little bit, it's a little bit glorified because 2 of the integrals are really very basic, but still one can do it. So if one has a derivative with respect to chi, well, the second term is actually going to, this is literally just going to be, so the derivative will vanish. And we can write out our matrix, which here has the form epsilon times chi 1 plus chi, and then minus 2, 1 minus epsilon over 1 plus chi, 2, 1 minus 2 epsilon, and then here we have 3 zeros, and again, in the equation for the bubble, it only depends on itself, and again, there's an explicit epsilon times f. So the key observation that Johannes Henn made a little over a decade ago is that it's possible to adjust the basis of integrals so that we can uniformly get a power of epsilon out front, and that's what's sometimes called moving to a canonical basis. So to do that, we're going to define the g functions, which are just related very simply in this case. In general, there's a matrix that will relate the 2 bases, whatever basis came out of the IBPs, and what is the basis that's good for the differential equations. So we're just going to scale out, in this case, a constant from F3. And when we do that, then we find something very nice. Then in this case, and in many cases, although not every case, or I should say, it's not necessarily known how to do this in every case. There are actually codes that will do this in the single variable case and in, I think, a large subset of multivariate situations. But this is, and so in some cases you have to find the relevant transformation, the analog of what's here, just a rescaling. You have to find it still by hand. So this thing you can simplify a little bit further by partial fractioning. And again, here that's a trivial thing to do. In general, that is not going to be the case. So here, once we've partial fractioned, then actually the relevant matrices just contain constants. So these expressions here that show up in the denominator, here it's just chi and 1 plus chi, they're called letters. And more generally, the set of, in general, rational functions that play these roles is called the alphabet that's associated with a differential equation system. But the key point here is that we have an overall epsilon in front, and so we can solve this system order by order in epsilon. So in the case here, the G2 and G3 are actually sufficient to fix the boundary conditions. Otherwise, you would have to look at values of the integrals at some special value of the arguments, and that, in the most complicated cases, might turn into another subsidiary set of differential equations. And so here, we can just write down the value for G2, which is basically involves the well-known kind of combination of gamma functions that shows up at one loop. And this thing, in fact, I don't know if the C gamma is supposed to include the 4 pi's or not, but anyway, that's how I'm going to use it here. And G3 is very similar. Of course, it's T-channel, so that is being kept track of through a factor of chi to the epsilon, and then the same constant shows up there. So we know that on general grounds, F1 is actually going to go as 1 over epsilon squared, and we've multiplied by an epsilon here, so G1 is going to go as order 1 over epsilon, and we can write each of the GI as a C gamma in front, and then we can write it in terms of powers of epsilon starting at epsilon to the -1, and then there's some coefficient. Let's see here. Yes, put that there. So this is the J, the indexed by J. And we can see that, in fact, G minus 1 is a constant. And so if we look, for example, at d by d chi, this is already beyond the constant, it's the next order, then it's going to have the form 1 over chi times minus g1 minus 1 minus 2 g3 minus 1. That's multiplying a 1 over chi. And then there's another term, which again involves this unknown constant plus 2g2, same order, and plus 2g3. Chalk is a little bit slippery in that corner. I hope this is legible. But this is just coming from this line of the second matrix. Now, if we look at the second term, then we can see that it would be singular as chi goes to -1. That corresponds to a singularity, which would then translate into a branch cut. So if we integrate this with respect to chi, we're going to get a logarithm. So there would be a branch cut at u equals 0. But if we go back and look at our original integral, there is in fact no possibility, there's no physical possibility of getting a branch cut at u equals 0. And the only way that that branch cut can be avoided is if this thing vanishes. And so that then allows us to fix G1 in terms of G2 and G3, which we know because they're part of our boundary conditions. And you can then go on and solve the equations order by order. And I'm going to let you do that as an exercise. Again, you're going to use the supplementary information about the singularities that should or shouldn't be there in the U channel to get some constraints. So that I'm going to leave as an exercise. Compute the next orders of G1. In fact, it's, I think, a nice exercise to go all the way through order epsilon. That's already an order where you don't need it, but it's a good working out of of your understanding of how to continue doing this order by order. So the general form that one can often get in modern systems, and there are integrals that are beyond the scope of this simple structure. We're going to get some constants, and then we're going to get some elements of what I've already said is called the alphabet. And in general, the change of basis you need to make is more than just multiplying the integrals by something. So in general, the change of basis going from f to g is going to involve some matrix. I may actually have these backwards, but that's going to take the coefficient matrix to some other matrix, which is given by something like a gauge transformation. So it looks like, in general, it has this kind of form where this is like a gauge, it's reminiscent of the way a gauge transformation looks. And there's a large class of integrals, I mean, things that are let's say, of the simplest category that that can be done this way. And the reference, by the way, for the paper which kind of first introduced this order by order approach is Johannes Henn, and that's from 2014. So the integrals which can be done in terms of generalizations of the functions that we saw yesterday, these are what are called Goncharov or generalized polylogarithms. these are iterated integrals of rational functions. So if there are more complicated letters here, things involving square roots, for example, then you may not be able to put it into this kind of form, and that's where the opening to more complicated classes of integrals like elliptic integrals or Calabi-Yau integrals or things like that comes. But if they are expressible in terms of Goncharovs, then the Goncharovs have a set of indices, and then there's one variable which it's a function of, and we just define the case of all zeros to be an nth power of a logarithm, and then with a single index, it's basically just a single integral of a rational function. So in this case, just a logarithm. So z minus a. Whoops, it should be t. My apologies. And then if one has a sequence of these indices, then one just iterates the integration. And there, sometimes you'll hear the words Chen iterated integral, which is a very closely related concept. So we have the first t minus, the first factor in the numerator, and then the function you're integrating is the Goncharov with the remaining indices. And of course, it's now a function of t, the thing you're integrating over. So these are the generalizations of those classical polylogs that we saw yesterday, and they're sufficient to compute a very large class of Feynman integrals, not necessarily everything that you will encounter if you're really doing frontier calculations, but a very large subset of them. So are there any questions before we switch to the last topic of the lecture series? Yes.
Okay, of course I know what you're alluding to in terms of the limitations of the polylogarithmic structure there.
Right.
But
I mean, you know all this stuff because you've been working on it, but not everyone else does.
Exactly,
so.
but I still have a question about it though. So if you have, in the case where it's still polylogarithmic,
yes.
If you have many square roots in your alphabet,
so sometimes it is possible to rationalize those square roots, and I'm not actually sure that there's a fully worked out criterion for when this is possible or not. I think that in practice, if you have like one square root, then you can rationalize things, and if you have more than a certain number, then you cannot, and in between, maybe you can be lucky, maybe you won't be lucky. And in general, if you have nested square roots, that's problematic, but sometimes you can get lucky. I don't know if, I mean, there may by now be a kind of framework for deciding algorithmically whether or not you can rationalize things, but I don't know it.
There are some algorithms for rationalization, but I guess the question is really whether these functions are well defined even for algebraic letters.
What do you mean by that?
So say you don't rationalize the square roots by some change of variables, can you just stick them in these arguments and the Goncharovs will be well defined? I mean, we can talk about it later.
I'm not really sure. There's a number of subtleties which I'm completely ignoring here, which is that implicitly one is thinking about defining these integrals in the Euclidean region where all the invariants are negative, and then doing some analytic continuation. And when one does these analytic continuation, one will cross branch cuts, and to understand the discontinuity prescription can be, in principle, very complicated. And indeed, complicated enough that some of the kind of frontier calculations do things differently. They try to have different definitions in different regions so that you never actually have to cross a branch cut. And then sometimes rather than doing things in terms of Goncharevs, it's actually better to have a low dimensional integral representation because you also have the question of how exactly should you compute the Goncharevs efficiently. And for the classical polylogs, there's a trick that is, as far as I know, due to a 't Hooft, which allows you to get an exponentially convergent series for them. But that trick does not work for the more general Goncharevs. And there, I'm not an expert on the efficiency of algorithms. I don't know if that answers the question or not.
Maybe we can talk more about it later, but
sure.
That was interesting. Thanks.
So the last topic that we're going to look at is that of massive spinors, or spinors for massive momenta. So it's something that I pushed off in the very first lecture when we introduced spinors for massless momenta. And that's at least the formalism which I'm going to show you. There are kind of other ways of dealing with it which people used in the past, which have occasionally some advantages, but they're certainly not as slick as the formalism that I'm going to show you, which is due to a paper by Nima Arkani Hamed and Yutin Wang and a then student also named Wang. And that's 1709, so it's not quite a decade old. Now, at least the original version of that paper, let's say the attention that was placed to signs and other factors was not always there. So that may have been corrected in a later version. I can't say for sure since I've never gone through the later version carefully. But there's another paper which applies some of these ideas and whose appendices actually are much more careful in all the signs and the conventions and the factors. And so I think that one is reliable. And so if you ever have any doubts about the signs or factors in this paper, then you can look them up in the second paper, and it should be reliable. So our starting point is the same as before. We construct a matrix by dotting our momentum into the 4-vector of extended Pauli matrices. But the difference is that now our determinant is still equal to k squared, but now that's equal to m squared, and it's not going to be 0. Well, that's okay. It just means that the matrix has rank 2, and so we can't express it as the outer product of two spinorial objects. We need two independent ones. So let's just do that. Let's write it down as a lambda spinor, and we're going to introduce another index to sum over. Actually, let's put this index bottom. lambda tilde, and we'll put that down there as well. We're going to contract over this new index I, which also is taking the values of 1 and 2. So in the case of in the massless case, we had a little group where at least the relevant part of it for transformations on the spinner was an SO2 or a U1, and that gave us the helicity. Here, if we go to the rest frame of K, something that we could not do in the massless case, but we can do here, then we can do a full rotation, not just rotations in the transverse plane. And so the little group here, at least at the algebra level and ignoring translations, is going to be SO3, which modulo double copying is the same thing as SU2. So it's natural to associate this extra index, so these things form a doublet under SU2. It's natural to associate that index with the little group. And then we still have the question of how to label the particle states. So in the massless case, we had the momentum and then we had the helicity here. Here, let's say if we were doing kind of non-relativistic quantum mechanics, then we would typically label the states by the total angular momentum, or let's say the spin if they're not orbiting something, and maybe by the component in some preferred axis. And that's, of course, not relativistically very friendly because we don't want to pick out a specific axis. But we can observe that the particles are going to lie in some representation of SO3 or equivalently SU2. And in fact, the spin S representation is going to correspond to having 2S indices, and it's going to be a fully symmetric representation of SU2. So, for example, for a 3-point amplitude, if we had, let's say, two massive spin 1 particles and one massless spin 1 particle, then, and let's say the massive ones are 1 and 3, and the massless one is particle 2, then it's going to depend, and I'm going to use the braces for symmetrization because that's what Arkani Hamed and the two Huangs did. It's not, I don't think it's very standard in the prior literature, but it does. So we're going to have 2 plus 1, and then the third particle again is spin 1, so it's a symmetric 2-index tensor, but of course the indices are different. And in the same way that helicity state carries, it's just part of the information, plus or minus helicity, here they're going to be, the particle is going to live in one of the states of the massive particle, and so it's going to have either 1, 1 or 2, 2 or 1, 2 plus 2, 1. There's 3 states, and you have to specify the polarization of that state coming into your scattering amplitude. So if I were to generalize this incidentally to something other than just spin 1, and that's something where the massless and the massive cases are different, then this H has to be within the range from -2 to 2 because there are no interacting theories of higher spin particles that are consistent. And I won't go through that demonstration, but you can show that by trying to construct a 4-point amplitude and showing that it's just not going to have a consistent factorization. So there are a few other things that are different from in the massive and massless case. So in the massless case, then we had this identity. I'm sticking for a little while to the kind of index notation, but we will get rid of it in a few minutes. So we also have this should be a dot. So this is kind of the kinematic form of the Weyl equation. And there's no, other than complex conjugation, there's no real way of getting from a lambda to a lambda tilde spinor. But in the massive case, the equation has a different form. So it's, I mean, in a certain sense, really the Dirac equation rather than the Weyl equation. And so we can have an equation of this sort. So that means that at the price of dividing by m, we can actually trade one type of spinor for the other. And it's clear why you can't do this in the massless case, because the right-hand side would be ill-defined. But here we can do that. So that means that unlike the massless case, counting angles or brackets is not as significant. You can always trade one for the other. Now, just as in the massless case, it's convenient to drop some of the indices, we're going to retain the I index, at least for a little while, explicitly. Again, we're going to index things by the label of the external momentum, but we can suppress the SL2C indices. So in gluing together these spinors, by the way, there are now two epsilon tensors that are floating around. So one is the epsilon tensor that is associated, or that are associated with the SL2C, the Lorentz indices. And then there's also an epsilon tensor that's the SU2 of the little group invariant tensor. And so you should keep their roles distinct. I mean, they're both the same thing, but they play different roles. So the lambda tilde tensor will write with a bracket as before. And when we change the index, it corresponds to going from the ket to the bra, just as before. We're keeping the little group index explicit here, whereas we were able to absorb the helicity label into the convention for the bra or the ket. And of course, these objects have either upper or lower indices. One has to be careful now because the epsilon tensor is antisymmetric. So we still have the Gordon identity, really just a contraction with sigma matrices, rearrangement identity. And so we have, so for example, if we have K1, then we can write this and everything looks perfectly normal to all of you. But if when we're to do the contractions a little bit differently, there's a minus sign. And so you have to watch out for that. Again, if one were to take the spinor product of two objects that are actually identical, so with the same I index, let's say the first I equals 1, then we're still going to get 0. But we now have two of these things. So that means that if we write out spinor products of the same label, same spinor variable, but just with that index there, then we can get things that are non-zero. And this, in some cases, is useful to simplifying expressions or to writing things out. So for example, if we have AI, AJ, that spinor product, again, the spinor product is, in this case, constructed with the same SL2C invariant tensor that we did in the massless case. This thing is now proportional to the mass, and the only thing it could be is the invariant, the little group invariant tensor. And one has to keep close track of whether the indices are upper or lower in order to get the signs right. So for the bracket product, it's actually with the lower indices. Of course, one can contract these indices as well. One contracts them with the epsilon tensor, and so you'll get expressions of this sort. The spinor product of AA contracted over I is equal to 2MA. So because of this relation, then one can choose to express the massive spinors, let's say, exclusively in terms of the angle spinors. Every time we see a bracket spinor, we could choose to convert it to an angle spinor. And so in general, if we have some expression, could be a part of an amplitude or just some expression that corresponds to, let's say, one massive particle, so it's going to carry in the spin S representation, it's going to carry two S labels. They're going to be symmetrized. So this thing we could choose to express exclusively in terms of the angle spinors. And of course, though they carry SL2C indices as well, so we now have 2S of those SL2C indices, and those, by virtue of the symmetrization of the little group indices, will end up being symmetrized as well. And the function f, of course, doesn't carry them, so this has to be contracted with some tensor, which then has to carry the SL2C little group indices fully symmetrized. And so f, if we have this convention, then f and t are essentially carrying the same information, and it can be convenient to, for example, we will write down the 3-point amplitudes first in terms of these objects before translating them to the spinor, the bra and ket notation. So there's one final kind of notational simplification we can do. So in general, if we have some higher spin state, some massive higher spin object, we're going to have a whole bunch of spinor products that are carrying each of the different indices. Each elementary spinor, of course, can only carry one index, so each spinor product correspondingly can carry one index of that and perhaps another index corresponding to some other particle, but only one index for that particle. So we're going to have a whole series of spinor products to represent the contributions there. So for example, suppose particle 2 had 3 indices, then, and particle 3 is massless, then we might end up with an expression of this sort. So there'll be 3 spinor products, and just for the argument's sake, they'll be symmetrized. And let's suppose at the same time that particle 1 also is massive, but it's a spin 1/2. This would correspond to, of course, a spin 3/2 with 3 indices. So it's going to carry a different index, but only one of it. And again, particle 4 is massless. So we can write this in a more compact form as 2, 3. Oops, let me write that a little bit more cleanly. 2, 3 cubed times 1 for bracket. And this also lets us write arbitrary spin expressions rather than writing it out. The 3 here would just be replaced with 2s, where s is the spin. So in print, this actually works nicely. These would be put in bold. These would be in bold. It's a little bit hard to simulate bold at the blackboard, so instead I'm underlining them. And of course, that underline has a very different meaning from the underline over here, so don't confuse the two. Okay, so we're now in a position to start writing down some amplitudes. There's many different cases that one could consider. The very simplest case is a 3-point massless amplitude. Incidentally, I just showed you the spin 1, pure spin 1, and pure spin 2 cases, but they're mixed cases, and I encourage you to go back to the kind of ansatz and then work out what, for example, a massless scalar interacting with a photon would look like, or a spin massless spin 1 interacting with a graviton, and all those things you can write down. So here we're not going to go through all of those. We're going to start with what's the simplest case, which is let's go back over here. Do it over here. Look at 2 massless particles and 1 massive particle. So this would be, for example, you could think of it as the decay of some massive particle to 2 photons or something like that. So let's think about 2 massless, and I'll label them as particles 1 and 2 with their respective helicities, and then particle 3 in the spin s representation. And it's going to be convenient, as I alluded to start by writing this down in terms of the t-tensor, and then we can convert to another representation. So associated with legs 1 and 2, we have 2 angle spinners. And because they're 2-dimensional objects, any others you could throw at me, I can write down in terms of those 2 spinners. They're a complete basis. So we can use them as a basis for our T-matrix. So we're going to have some constant, which we're going to worry about in a little bit. And then we have some number of powers of the first spinner, angle spinner, and some number of powers of the second angle spinner. And this thing carries some SL2C indices, which are fully symmetrized. In fact, there's 2 S of them. S here can be both integer and half integer, so 2S can be both even and odd. And then, in addition, we can imagine that there might be some spinor products that just involve the 2 massless momenta. Well, we know how many of these spinners have to be there because there have to be enough to give us the right number of indices. So that says that N1 plus N2 has to be 2s. And also the spinner weight overall has to give us the correct helicity, whatever H is. I mean, could be 1 or 0 or 2, and negatives of those. So we have two additional equations. So N1 plus EA minus EB, and then there's the helicity of the lambda spinner, which is minus 1/2. That should be H1, and there's a similar equation for N2. Again, N2 plus EA minus EB, minus 1/2 of that expression is equal to H2. So at first glance, there's a little bit of an issue here because we have three equations, as we've had before, but we actually have four different unknowns. So we have to do something there. And in general, of course, if we're doing purely massless things, the angles and the brackets play a distinct role. But we still have momentum conservation, and so K1 plus K2 squared is equal to m squared. And so that means that we can actually trade, in this case, while we can't trade the spinners, we can trade the spinner products at the price of changing the powers of m. But the powers of m at the moment are all still inside C because we're going to have to make this thing dimensionally correct anyway. So let's just choose to set EA equal to 0 and express things totally in terms of the bracket product of 1 and 2. So now we can solve the equations, and assuming in my sleep-deprived state I wrote down the correct solution, then this is what it is. So we have S plus H1 minus H2. And finally, EB should be S plus H1 plus H2. We can check that at least the number of indices is clearly correct. Excuse me. So the spinner part here has, so the dimension here, so this we're setting to 0, the dimension here is going to be S plus H1 plus H2. And here, each one is carrying 1/2, so the sum of these two is going to be 2s, but it's only going to contribute s, because each spinner is carrying energy dimension of 1/2. So the overall dimension here is going to be 2s plus H1 plus H2, but a 3-point amplitude should have dimension 1. And so in addition to some coupling, that means we have to divide out by a dimensionful scale. And so it's going to be m to the 2s plus H1 plus H2 minus 1. So that's what the constant is in this form. But we might like to have it in this kind of more compact angle and bracket notation. And here there's just, we can, again, later convert some of the lambda 3s to lambda 3 tildes, but the simplest thing is to first start just by writing it in terms of lambda 3s. And when we do that, we just contract this tensor with an appropriate symmetrized tensor of lambda 3s carrying the same indices. And then we're also, of course, multiplying by something dimensionful, so we're going to have to adjust the dimension, and we're going to find an amplitude that now has m to the 3s plus h1 plus h2 minus 1 in the denominator. And we now have whoops, bolding the wrong thing. So 1 contracted with bold 3 raised to the s plus h2 minus h1, 2 contracted with bold 3 raised to the s plus h1 minus h2, and finally bracket 1, 2 raised. Here there's no hidden indices. It is just raised to that power, s plus h1 plus h2. So among other things, one can see that, for example, if you have an odd spin massive particle, then, and you take, let's say, the decay helicities to be identical or opposite, then this thing will be an even number, and this thing will then have the wrong symmetry. It'll be antisymmetric. If S is odd, it'll be antisymmetric instead of the desired Bose symmetry. So, and that's something you can immediately read off from this expression. This has the name of Yang's theorem. And I don't know how complicated that paper was in the original version many years ago, but I'm sure it was more impressive than just looking at one line of an amplitude expression. So the next amplitude we will look at is now where we have 2 massive legs. And just for symmetry's sake, I'm going to still retain the 2. Now I'll put the 2 massive ones as particles 1 and 2, and the massless one as particle 3. So now we have only one kind of massless spinner. So we're going to need to build another spinner out of something else. And there are 2 cases that we should consider. The simpler case, in a sense, is where the 2 masses are not equal. And here we can, for example, construct another spinner that we can build out of either K2 or K1. It doesn't really matter. Obviously, they just differ by a sign. So we build it out of the conjugate spinner for leg 3, which, if we're thinking in terms of complex momenta, again, an independent object from lambda 3. So we can believe that this thing is independent. So we now have, of course, 2 sets of SL2C indices corresponding to particle 1 and particle 2. And these I'm going to label using alphas, and these I'm going to label using betas. But the general form is going to be the same. There's, of course, nothing to contract lambda or lambda tilde with anymore. So we just have the T tensor with no additional factors of any spinor products. So we have n3 copies of lambda 3 and nu copies of u. And now we have 2 sets of indices, 2s1 of the alphas, and which are symmetrized among themselves, and 2s2 of the betas, which are again symmetrized between themselves, but there's no particular symmetry between the two sets of indices. And here you can again solve for the N3 and NU. You find that it's S1 plus S2 minus H, and NU is simply S1 plus S2 plus H. Still, you have one more thing you have to take into consideration, which is how should you assign the alpha indices to lambda 3 or to U, and how should you assign the beta indices to lambda 3 or to U? And the answer is that each different assignment is really a different coupling. It's a different fundamental interaction. And you have to consider all of them. So in general, there's more than a single amplitude here. There's more than a single coupling. So the final example we're going to look at is the case where M1 is equal to M2. Now, why is this actually different? And this, of course, is the case that's, let's say, the more common one physically, the one that's more relevant, at least for, let's say, applications in classical gravity and many applications in collider physics. So if we look at K1 squared, go back to looking at three-point kinematics, then we can write down this equation, which is going to be 2K2 dot K3 plus M squared, M2 squared. So in other words, 2K2 dot K3 is going to be equal to M1 squared minus M2 squared. So over here, that's some non-zero thing. But here, it's going to be 0. And that means that, in fact, we now have the following equation. So this is one spinner, and this is another spinner. It carries an alpha index. And the fact that their spinner product is 0 means that they are collinear. It means that they're proportional. So in fact, in the equal mass case, U and lambda 3 are no longer independent. And so we can't just do this construction. Of course, the same would be true if I were using particle 1 instead of particle 2. However, because they're collinear, just in the same way as if you had two collinear momenta, you can take their ratio. It's essentially equivalent to taking the ratio, for example, of the time components. Here, we could take the ratio of these two spinners. And that's something which, in the Arkhani-Hamid paper and probably elsewhere, is usually called X. And we can write this as follows. So this has the following form. I won't actually divide by spinner 3, because that might look a little bit strange, but that is implicitly what we can do here. So this comes in essentially two useful expressions, one for the bracket and the other for the angle. So this x here is a scalar, but it's a scalar that carries non-trivial spinner weight and carries non-trivial helicity. And it's kind of the ghost of this this linear dependence that emerges in the equal mass case. We can actually write an expression, a concrete expression for it if we introduce some reference spinner. So let's say if we introduce a reference spinner eta, then we can write x as eta 1, 3 divided by the mass times the angle product of eta and 3. And of course, you can see that this thing carries the same phase weight as bracket 3 squared. It carries no spinner weight under eta. So, but it turns out you cannot actually write an expression for this without a reference spinner. If you have sewn it into some higher point expression, then as in the case of the Chinese magic, you can typically choose some other massless momentum to be the reference spinner, and then you may get more natural looking expressions. So we have one object that carries SL2C indices. The only other object that we have that we could possibly play with is the epsilon tensor, the invariant tensor. So now we can write down some expression, some powers of this x. We'll write down some number of powers of lambda 3, and then some number of epsilon tensors. So this object now carries 2 indices. Each of these carries 2 indices. And it has to be 1 alpha and 1 beta index because its indices are anti-symmetrized, whereas within the alphas or within the betas, they're symmetrized. So if we were to put 2 alphas here, then the thing would just vanish. So you might wonder, why is it that I didn't use the epsilon tensor in this case, for example? And I leave that as a homework exercise, why that wasn't necessary. And again, here, you can see that we're going to get basically 2 equations for 3 unknowns. So again, we cannot fix these exponents completely. We're going to get a sum over a different set of interactions, a different set of couplings. So it turns out that N3 has to be positive. We're going to get a sum over J that has the form of some dimensionful coupling. I'll let you work out the dimension with this x to the h plus j. And then there's 2j of the lambda 3 spinners and S1 plus S2 minus j epsilon symbols, and then with those sets of indices. And the sum here is going to run, I think, from something like S1 plus S2 minus the absolute difference up to the sum of S1 and S2. Okay, I'm going to run a few minutes over and just kind of sketch out one factorization argument. So I'm not going to have time to discuss the massless limit or the high energy limit, but roughly speaking, each of the massive spinners has to contain both of the helicity choices in that limit. And so if you try to do a shift of the massive spinners, then sometimes it can work, but in many cases, especially in the low point cases, if you're trying to shift two massive legs, for example, then you may find that there's no option that has good large Z behavior. And then you're stuck with trying to construct 4-point amplitudes, for example, by factorization, by sewing together or by writing down an ansatz and exploring the factorization. So if we look at, for example, a graviton Compton off some spin S particle, and here I'm going to take the two spins to be the same for simplicity, then we can imagine looking at the factorization in the S channel. It's going to have the form 1 over S minus m squared, and then we're going to have a product on the pole, a product of two 3-point amplitudes, which they're going to be equal mass. We're not changing the mass here, so it corresponds to the thing that we've just written down. And if we take the simplest of the couplings, so what is in some sense the spinorial definition of minimal coupling, then we're going to get something of the form, and I'm going to attach the x variable. I'm going to call it x over here and y over here. Then we can write this, and this is the label P. So we can write this as the angle product of 1p understood in this kind of tensorial sense on one side, m to the 2s minus 2, and then we have 1 over y squared, and again p4, again in the same tensorial sense from the right-hand amplitude. And finally, we have, of course, the propagator. So one's going to sum over the indices of this exchanged line. That will sew this together into a single spinor string. And we're going to get x squared over y squared. And there'll be a spinor string still raised in this, still understood in this tensorial sense for the indices of 1 and 4. We can work out what x is here, and here it's useful to use that representation. Although here I will call the reference momentum rho and rho and xi, just for variety's sake, to exercise the Greek alphabet a little bit. And here I can choose, of course, different representation. Well, I have to use different momenta because it's a different amplitude. And I can choose different reference momentum. There's no particular reason they have to be the same for different factors. So this is 3 and xi. And just to line these things up, then, and to make them nice, I'm going to choose a momentum from the other side, a massless momentum from the other side of the factorization for rho, and likewise for xi, something from the other side. So there's no, I'm not allowed to choose, of course, the same massless momentum. That would give me, so I can't choose 2 for rho because that would give me a singular, that would result in a singular expression. And so then x squared over y squared is simply going to be the 4th power of a certain spinor string, spinor sandwich, and there's some number of powers of the mass that we get as well, and there's a t squared. it turns out, using the properties of the massive spinner, I guess I didn't finish writing out the powers of the mass here, which is 4s minus 4. So the minus 4 will be eaten up by the 4 over there. We can rewrite the spinner string. In fact, in a certain sense, we are obliged to write it out in order to see its full analytic structure. So we have 1p4 divided by m squared is equal to 4312 plus 1342. And you can see here already the kind of way in which both of the helicities would emerge if you were to take, if S were small enough that you could take the high energy or equivalently the massless limit, you would get one of these two terms that would show up. The thing that this rewriting reveals is that you get this very odd spinner string in the denominator. So if you put this thing together, you put this ansatz together, then for our 4-point amplitude, we get 1 over s minus m squared times t squared. And we can symmetrize this spinner object, if we so choose, by averaging over the two choices of 1 and 4. That doesn't really matter so much. And then we have this times that object over there tensored in the way that we've seen for the indices of the two higher spin particles, or the two arbitrary spin particles, massive particles. So there's two problems here. And this thing is raised to the 2s power. There's two problems here. First is that this can't be right. T squared is not something that can show up in a factorization. Remember that when we discussed factorization, we just had a single power of an invariant in the denominator. But the solution here is relatively simple. We're sitting on the S-channel pole. And so there, of course, we can trade t for a power of u minus m squared. So even though we haven't done a U-channel diagram, then, and this was actually true, I perhaps should have pointed it out in some of the BCFW things, that you get kind of for free the appearance of poles in other channels. So here we can replace that t squared with a t times, let me write it out over here, u minus m squared. And then you have the kind of typical thing in a gravitational amplitude of having an st and u. The other problem is that if s is too large, it's going to overwhelm the factor in the numerator for this strange spinner string, which is not a physical singularity. And so this ansatz is actually perfectly fine as long as 2s is less than or equal to 4, or s is less than or equal to 2. That is, if the massive particle has spin 2 or less. But in many applications, you want to consider higher spin. And there really is a pathological singularity, which these gentlemen here showed how to fix up. You have to add in contact interactions, and that the need to do that is, at the end of the day, not so surprising, because for higher spin massive particles, there is no massless limit. You're always working in the context of an effective field theory. And so you should always be expecting to have some tower of contact interactions. And here, they're actually going to be essential. They're going to be relations between the couplings of the fundamental interaction and these higher dimension operators in order to get something consistent. Of course, if you'd started with some underlying theory and integrated things out, that would have emerged for free. So with that kind of introduction, quick introduction to massive spinners, let me actually stop here and also close this introduction to scattering amplitudes.
We have more time for questions in the afternoon. After the coffee break, we reconvene for the closure and discussion. But if you have some doubt you don't want to dwell over.
Yeah, be sure to ask the afternoon questions early at, I guess we're starting at 4:30?
Yes.
Yeah, so try and ask them in the first few minutes because I'm going to have to disappear afterwards.
So don't wait until then.
Yeah, if we are defining the massive polarizations can come with two little group indices, right? So let's say for massive particle 1, I define epsilon 1, 1.
Well, I mean, that would be the case if it were spin 1, right? I mean,
Yeah,
in general, the polarization tensors will carry many.
Yeah.
Right.
I'm just saying, if you're considering just spin 1 particles, and we have little group indices which are the same, it's pretty direct how I will define polarizations. But if I have different little group indices, let's say 1 and 2, then I have to symmetrize it.
Yes.
And for polarization, I understand that. But when I'm writing down 3-point amplitudes, where you have written down somewhere like 1 to the power 2s or something like that, how will I explicitly write little group indices there?
So again, this is just a shorthand, right? So let's say if S, for example, were 2, so this thing were raised to the 4th power, and you had some expression like 4/3 to the 4th power, that would be an indication that this thing is a spin 2 and it's carrying 4 indices. And what that actually means is 4 to the, let me call those indices, label them with I, 1, and so on and so forth, be 4/3, 4I2, 3 times 4I3, 3 times 4I4, 3. And these indices would all be symmetrized.
But if that is 4/3 to the power 4, I understand that. But in this case, I have a total thing to the power 2s, right? So how would I symmetrize that?
I mean, you write out 2s copies of them, and then the indices are going to be symmetrized for the 4. I mean, here you're essentially symmetrizing simultaneously in the I and J indices.
So, for example, if I'm saying this because let's say I write 4/3 and 1/2.
Yes.
So I can write 4/1/3, 1/1/2, multiplied by 4/2/3, 1/2/2.
No, I mean the SL2C indices, the spinner indices, are contracted in this way.
Yes, yes.
The thing, I mean, the little group indices are implicit here. They're free indices. They would have to be contracted with whatever the wave function of the external state is.
Yeah, so maybe if I write it down, maybe I'll ask it later.
Okay.
If that's okay, yeah?
Okay.
Yeah, hunger is taking over. So let's thank David for the whole set of lectures. As usual, we reconvene 2:30.